You know, from the massive engine in a jet to the tiny gears in your car, there's this invisible backbone holding our modern world together, specially treated steel. But have you ever wondered how we get this everyday material to do such extraordinary things? Well, it all comes down to a process that's part ancient art and part cutting-edge science. We're talking about heat treatment. So let's dive into how this incredible process has evolved. And that really gets us to the core challenge, right? It's this constant balancing act between making steel unbelievably strong, but also keeping it microscopically precise. If you get it right, you've got a part that can handle almost anything. But if you get it wrong, the results can be disastrous. So, how did we get here? For centuries, the secret was all in the hands of skilled craftspeople. But today, it looks a whole lot more like this, a huge, complex industrial-scale operation. We're going to trace that whole journey, from the gut feeling of a blacksmith all the way to a thinking machine. All right, let's start at the very beginning. A time when heat treatment wasn't about charts and sensors, but was a true art form, something you could only master through years of feel and intuition. I mean, think about this. A blacksmith would heat a piece of steel and just watch the colors, seeing it glow from red to orange to a bright yellow, and they knew, instinctively, what each color meant. And they had this amazing trick. They'd touch a magnet to the hot steel. When the steel got hot enough that its internal structure literally started to shift, it would stop being magnetic. That was the sign. That was the moment to quench it. It was all based on pure physical observation. Incredible. And this quote, wow, it just perfectly shows the deep, almost personal connection that experts develop in this field. It's not just a 9-to-5 job. For a lot of people, it really becomes a calling. The field is so complex, so specialized, that it kind of pulls you in and can end up defining your entire career. So if we're going to put a simple definition on it, what are we really talking about? Heat treatment is all about controlled heating and cooling. That's it. By playing with that temperature cycle just right, you can totally change steel's properties. You can make it harder, tougher, more resistant to wear, whatever you need for a specific job. It's a fundamental part of metallurgy. Okay, so as we move into the industrial age, that blacksmith's touch gets replaced by standards, by specifications, by scientific principles. And that brought a ton of consistency, which was great. But it also uncovered a really frustrating problem. Sometimes, even when you follow the rules to the letter, things still go wrong. Take a look at this high-performance gear. I mean, this thing is engineered and built to incredibly exact specifications. It passes every single quality check you can throw at it. And yet, under totally normal conditions, it can still break. So what's going on? Well, the answer is hiding at a level you can't even see. In one real case, a gear like this failed because the hardening process was run just a little bit too hot. That extra heat created these coarse, brittle grains deep inside the steel's structure. So, on paper, the gear looked perfect, but in reality, it was hiding a fatal flaw that none of the standard checks could catch. And you know, the problem isn't always microscopic. Sometimes it's a simple operational choice. In this example, a plant wanted to boost its output, so they started stacking more baskets of parts in the furnace. They went from 5 baskets to 7, which was a 40% increase in the total weight. But they didn't change the heating time to account for all that extra mass. And guess what? The whole batch failed. And that's the kicker. Even small, logical changes can have these huge, unexpected consequences. This is where the story gets a 21st century upgrade. How in the world do you manage all of these variables at once? Temperature, time, weight, shape, the microstructure. Well, the answer is you fight that complexity with a tidal wave of data. And this is where the AI assistant comes in. By feeding machine learning models just enormous amounts of information, from sensors, from old process logs, from our scientific knowledge, these systems can start to see patterns. Patterns that a human operator or even a whole team of engineers could just never spot on their own.
And the impact it's just transformative. We're talking about AI optimizing the whole process for better quality while using less energy. It's doing quality control not at the end, but in real time. It can even predict when a furnace is going to need maintenance before it breaks down. It makes things safer, and it gives engineers the data they need to make way smarter decisions.
And that leads us to the real game changer here. It's about moving away from educated guesswork and getting as close as we can to a guarantee. The numbers on this are what really tell the story. Okay, just look at this. It's wild. The traditional math equations we've used for decades to predict heat treatment outcomes, they're pretty good. They have a correlation accuracy of around 0.7 to 0.85. But the AI models, trained on all that real-world data,
They're hitting correlations of over 0.98. That is a massive, massive leap in how predictable this all becomes.
And it's not just about being more accurate, it's about being ridiculously fast. These AI models can run complex simulations up to 10,000 times faster than the old methods. This isn't just a small improvement. It makes something entirely new possible: real-time control. The system can literally see a problem developing and correct it on the fly while the process is still running. So, what does all this speed and accuracy actually get you? Well, here it is: a huge reduction in variability. We're seeing that AI-assisted processes can cut down on the variations in the final steel properties by up to 70%. What does that mean in the real world? Fewer defects, less wasted material, and a much more reliable, consistent product every single time. Now, when you have a tool this powerful, it's totally natural to start wondering about the role of the human expert. I mean, does this amazing technology mean the engineer is on their way out? Let's just tackle that question head on. If an AI can predict, control, and optimize the process better and faster than a person can, what's left for the person to do? And this is the part you really have to remember. The AI is only as smart as the data we give it. And where does that data come from? It comes from 100 years of human experience, of trial and error. So the AI can work brilliantly inside the box we create for it, but it's the human expert who understands the physics, who builds the box, and who knows when a result just doesn't make sense in the real world. This quote from an industry expert just hits the nail on the head. AI is an incredibly powerful tool, an assistant that can see things we can't. But it's not perfect. The final call, the sanity check, the judgment, that still has to come from an engineer. The human is the essential bridge between the digital model and the physical world. So we end not really with an answer, but with a new, really important question. We've traced this journey from the blacksmith's intuitive touch to the AI's complex algorithm. The next big step isn't about choosing one over the other. It's about figuring out how we build the absolute best partnership between them, how we combine a century of human wisdom with the incredible predictive power of a machine. Because that partnership, that's the future of how we make things.